Thank you very much. Let me start out by telling you a little background about the planet Mars and why we care, and how we have come to know what we do about the planet Mars. So for the vast majority of human history, this has been our understanding of Mars, a bright red dot in the sky that moves slightly differently from the way the rest of the stars do. And this has been our knowledge and experience of Mars for most of the time that humans have been thinking about Mars. And even 100 years ago, even after the advent of relatively high-powered telescopes, this was the best image that we had of Mars. This was as much as we knew about the world that might be Mars. And even right before the dawn of the space age, this was our best image of Mars. Really nothing more than a disk in the sky with some various shades of reddish brown and a hint of polar caps on the top. And so it's not hard to see why, with only this amount of information, the imagination went wild. And in the 1950s, we really had this explosion of science fiction stories about the peoples of Mars, because we really didn't have much to go on other than this planet that was a world that had various colors and shades on its surface. And so it wasn't just science fiction that believed that there were these possibilities for the planet Mars as being a place where things could live and thrive. It was even among the scientific community that it was generally accepted that Mars could be a world that was alive with life. I want to read from you an excerpt from The New Yorker, a Talk of the Town piece from 1956. And it says that, what are the astronomers particularly anxious to observe on Mars this week? Well, there's a green patch that used to be orange. If they get some clear spectrograms of it, they may be able to tell whether it's vegetable or mineral. Furthermore, a cloud formation shaped rather like a W has been seen floating above the canals. How come? Mars has no high mountains, and its deserts are thought to be of rock, not sand. The broad green areas to be observed on Mars were once thought to be seas and maybe mineral deposits, but the best guess is that they consist of prairies of lichens and mosses. Anyhow, they change color with the seasons about as our lichens and mosses do. So this was the generally accepted scientific opinion of Mars as not a place of monsters and creatures, as was described in the science fiction novels, but a place where there could be vegetable life, plant life, very similar to vegetation as we know it here on Earth. So a place still filled with possibilities for life. Now, the first spacecraft that we sent to the surface of Mars, the Viking landers in the late 1970s, took pictures that revealed a surface that was not covered with lichens and mosses and vegetation, but rather a surface that looked like a reddish version of what the Apollo astronauts had seen on the moon. We have these mainly lava rocks, volcanic rocks, that look like they've been busted up by impact craters on the surface. And there's no evidence here that water flowed on the surface. There's no evidence here that there had ever been vegetation here on the surface. So these first ground truth images really dashed the hopes of there being a Mars as a world that was alive and thriving with life. And even 2 decades later, the Pathfinder lander, with the little Sojourner rover you see in the picture here, showed more or less the same story. And Pathfinder was chosen to be at what looked like it should be the outflow of a giant channel on Mars. This is where we expected to find lake deposits and all sorts of interesting sedimentary rocks. But Pathfinder again found what looks like a barren moonscape. Now, Mars was still becoming a more and more interesting planet, however, to the scientific community, because in addition to these landers at very unfortunately boring places, we had orbiters circling the planet, taking high-resolution pictures and revealing the scars of ancient river valleys on the surface of Mars, and even very small-scale gullies that look like they had to be very young, formed relatively recently on Mars. So we knew from these scars of former water having flowed on the surface that Mars had to at least have been, at some point in its history, more interesting than it is today. And with the higher resolution cameras that came about around the turn of the century, we got our first glimpse of sedimentary rocks on the surface of Mars. Rocks that form from layers at the bottoms of giant lakes, from rivers, from wind-blown dust and sand, rocks that form from active geologic processes much different than is possible on the moon. And we even saw evidence for preserved deltas, ancient river deltas that had fed into giant lakes on Mars. And this was the first smoking gun evidence that not only had water flowed across the surface of Mars, but water had been long lived here in order to form these huge sedimentary deposits. So we knew from the orbiters around Mars that we had this at some point. And we knew that Mars, even though it's this dry, barren, desert, cold, lifeless world today, we knew from that evidence of our orbiters circling the planet that Mars a few billion years ago may have looked more like this. And this is the Mars that we're interested in. This is the Mars that we think was geologically active, geologically diverse, that had carbon cycles, that had hydrological cycles, that had the conditions that might have been favorable to early forms of life. So we're not looking for mosses and lichens even anymore. On Mars, we're looking for the most primitive, single-cell forms of life, and that would still be an enormous discovery. And we think, from everything we're learning about this version of ancient Mars, that that could still be a possibility. So let me show you a little bit about the diversity of the planet Mars, and here's where you get to put on your 3D glasses. I'm going to give you a tour of Mars from orbit with one of the highest resolution cameras ever sent to another planet. And this will give you a sense for the incredible diversity of sediments that are on the planet Mars. And it's really not going to look like a moonscape anymore. So here's a region of sedimentary rocks that have since been sculpted by wind. These are rocks that we believe formed in an ancient river and lake bed system that have since been sculpted into these patterns and hills and buttes by hundreds of millions of years of wind. Here's another example of an enormous stack of layered rocks on Mars. And again, these pictures are going to pop a lot better when the light is completely off, so maybe we can try that at the end of the talk. Another example of spectacularly layered rocks on Mars, sculpted by winds in the past hundreds of millions of years into very dramatic landscapes. And finally, this is a sea of sand dunes on the surface of Mars. And these are active today. The water cycle has shut off. There's no liquid water on Mars today, but there are still seas of sand blowing around the planet. And this is the most active geologic process occurring on the surface of Mars today. So glasses off. That just gives you a little taste of the diversity that's been revealed on the surface of Mars. And it's that diversity and that ancient period of Mars's history when there were sedimentary processes, lakes, rivers, that we hope to uncover the secrets of with our robot army. So this is NASA's Rover family portrait. The little guy in the middle is the Sojourner rover, which went to Mars now nearly 20 years ago on the Pathfinder spacecraft. That rover was really a proof of concept that, yes, we can drive a robotic car on the surface of another planet. That mission was a great success, and it really paved the way for the Spirit and Opportunity rovers. They went to Mars in the year 2004. They were identical twin rovers, went to opposite sides of the planet. They were designed to last for 90 days. And today, Opportunity is still going well into its 11th year. So arguably NASA's greatest success story. The Spirit rover didn't do too bad either. Spirit was also designed to last 90 days and lasted about 7 years. So both fantastic successes. What I'm going to talk to you in depth about today is the Curiosity rover and its mission. Curiosity is the big, beefy rover on the right. And that one, we will talk a little bit about how it's different from the previous rovers and how it's really made some of the most exciting discoveries that any spacecraft has on the surface of Mars. The Spirit and Opportunity rovers, which went to Mars in 2004, one of which is still driving around today, these were the first robot geologists on Mars. These were not just proof of concept missions, these were mobile scientists that had suites of instruments that could examine the chemistry of the rocks, the mineralogy of the rocks, and the rover even had a small drill that it could use to grind into the surface of rocks to see what was beneath the outer dusty layers of the rocks. So these rovers were an incredible success, not just because they lasted so long, but because they told us so much about the surface of Mars. Now, these rovers were sent to Mars to follow the water. We knew from orbit that there was this history of water on the surface of Mars. There had been rivers, there had been lakes, but we didn't know very much about the quality of that water. We didn't know how long it had been around. We didn't know if that water was the kind of water that you and I could drink, or that even the hardiest microbes on Earth would be able to survive in. That water could have been very salty, very acidic. And what these rovers found was that while they had both gone to very fascinating landing sites where water had been interacting with the rocks at the surface, what we found was at the Spirit's landing site, the water that had been present was in the form of hot springs, very acidic hot springs, very similar environment to Yellowstone on Earth. The Opportunity rover went to an environment that had several millions of years ago in the past been a shallow lake. And that lake water had also been very acidic, about as acidic as battery acid. So while both of these rovers found evidence for water on Mars that had been there a while, it did not find evidence for water that was necessarily habitable, the kind of water that we expect life to have been able to evolve and thrive in. The Curiosity rover was sent to Mars in 2012 is when it landed, and it was sent to Mars to go beyond the question of water and start addressing the question of habitability. So not just was there water on Mars, what was that water like, but was Mars a place where life could have survived and thrived? And this is what Curiosity's mission has been about. And you can see that Curiosity, just at first glance, looks a lot different than its predecessor rovers. First of all, it doesn't have those black shiny wings. Those were the solar panels on the previous rovers. Curiosity carries its own power pack in its big caboose in the back. That's a radioactive power source that powers the rover, so it doesn't matter how dusty Curiosity gets, and the rover can continue to power itself through the night. So that's a huge advancement. This rover is also much bigger. It's about 4 to 5 times bigger, either the Spirit or Opportunity rovers were. And it has to be that big because inside the belly of the rover is a science laboratory, a mobile chemistry lab. And what that rover can do is tell us very precisely, more precisely than we've ever been able to before, what the mineralogy of the rocks is, which tells us what kinds of environments those rocks had formed in. And this rover, most importantly, can search for organic molecules on the surface of Mars. This is something that is extremely important for the question of habitability because organic molecules are the building blocks of life. And this is the first time that a rover on Mars has been able to make those detections. Now, you don't get a sense from that animation of just how big this thing is, but the Curiosity rover is about 10 feet tall. It has a robotic arm that is 7 feet long. It has a set of instruments at the end of that arm that weighs 200 pounds. It's about the size of a lawnmower, just at the end of its arm. It's so heavy that the rover cannot lift its own arm all the way up under Earth gravity. Only under Mars gravity, which is 3/8 of what Earth's gravity is, can the rover lift its arm. That's how big this thing is. This rover is also so heavy and so large that NASA had to design a brand new landing system from scratch because we had never delivered a payload this beefy and this delicate to the surface of Mars before. So let me show you an animation of what this rover landing on Mars looked like. The rover weighs about 2,000 pounds. And as it's arriving at the upper atmosphere of Mars, it's traveling about 14,000 miles an hour. Now we have to slow that down to about 2 miles an hour to have a gentle, soft touchdown on Mars. So you see the spacecraft entering the top of Mars's atmosphere. The heat shield in the front prevents the whole thing from burning up. And then you'll see a parachute deploy, the largest parachute ever sent to the surface of another planet. And this parachute had to be so large because Mars's atmosphere is so thin, about 100 times thinner than the Earth's atmosphere. Enormous parachute. I have a piece of parachute fabric up here at the front. Come, feel it, see if you can rip it apart after the talk, and I think you'll be impressed with how lightweight and strong this space-age fabric is. After the parachute detaches, there is a jetpack on the rover's back that fires up and starts slowly lowering the rover down to the ground. But it's only going to take the rover so far. It's going to lower it down to a point, and then the sky crane mechanism is going to kick in. Now what we're zooming in here is a camera on the belly of the rover looking straight down, taking high-definition video the entire time that the rover is landing. Now the jetpack is hovering, and the rover is being lowered down on 3 tethers. This is called the sky crane maneuver. This is the new part of this whole system that had never been tested before on Mars. The sky crane lowers the rover down to the surface, and notice that the rover lands on its wheels. So we really want that to be a soft landing. Then those tethers detach, the jetpack flies away, and crashes into the surface, hopefully far, far away from the rover. So you can imagine why this made a lot of people nervous. This had never been tested before. It couldn't be tested under Earth gravity. The landing system requires the rover to land on its wheels, and we have to use those wheels to drive. So if this landing was a little too hard, we'd find ourselves with a lander, not a rover. So it was really important that this system work. And a lot of folks were really nervous, not just because this system was new, but because Mars is a really difficult place to land on. As of the time that Curiosity landed, there had been 14 attempts by the US, the UK, and the former Soviet Union to land spacecraft on the surface of Mars. Only 7 of them had worked. So that's a 50% rate of success. And when you're talking about sending $2.5 billion worth of very delicate spacecraft to the surface of another planet, those odds themselves cause some heartburn. So understanding that, I'm going to show you that little landing animation again, but this time it's spliced with the real-time footage of the engineers at NASA's Jet Propulsion Laboratory who were monitoring this whole system as it was taking place on the evening of August 5th, 2012. So you'll see them all in their blue shirts looking very tense and very nervous. This is called the 7 minutes of terror, because after more than 7 months, about 9 months actually, of traveling through space to get to Mars, it takes only 7 minutes to get from the top of the atmosphere down to the surface. Now there's the parachute deploying. The engineers have registered the success of the parachute. Heat shield detaches, falls to the surface. And there's a 7-minute time delay between the Earth and Mars, on average. So everything that's happening here, when the engineers get feedback that something worked, it actually had worked 7 minutes ago. And I always thought that was disturbing, that if we heard that the rover had crashed, it had actually crashed 7 minutes ago. Okay, now here's the part when folks are getting really nervous, the sky crane maneuver. Everyone's pretty tense, waiting for the good word. Yeah! While this was happening in the engineering room at JPL, I was in the largest room on the JPL campus with the 400 science team members. And us scientists were in there just as tense. And when we heard the words Tango Delta nominal, that's touchdown nominal, that's the code for yes, it worked, I have never seen so many grown men cry in my life. It was amazing. And there is the first picture that the rover sent down with the wheel. You see the wheel in contact with the surface. An amazing moment. So where did Curiosity land? Now that we know it got there safely. Curiosity was sent to land in an enormous crater called Gale Crater. And the reason it was sent to this site in particular is because there's this huge mountain in the center of the crater. Now, this mountain is not related to the formation of the crater. This is a mountain of sedimentary rocks that formed long after the crater was created. 5.5 kilometer high stack of sedimentary rock. So that's on par with the height of Mount Rainier. So somehow, some process brought all of this sediment, all of this rock into the middle of Gale Crater after the crater formed. And we think that one of those processes was most likely water. And we know that because there is such a huge stack of rock here, here's a cross section through that crater, because there is such a huge stack of rock, it must have taken long enough for this mountain to form that the rocks at the bottom are very, very old. We think the rocks at the bottom of the mountain are about 3.7, 3.8 billion years old. That's that early period of Mars's history when we know that there were rivers, lakes, active water. That's the period in Mars's history where we think if life had ever emerged on Mars, it was then. And the record of that life might be stored in the rocks at the bottom of this mountain. As you go up the mountain, the rocks get younger and younger, and towards the top, the rocks are only a few 100 million years old, which to us Mars scientists might as well have been yesterday. So we have a stack of rock that essentially encapsulates the most interesting periods in Mars's history from the bottom to the top. And so this mountain was an opportunity for the rover to drive through geologic time on Mars, from the oldest, warmest, wettest era of Mars's history up to the Mars we know today. And let me just mention that the circle here, the oval at the bottom of the crater, that is the rover's landing ellipse. So we knew that the rover was going to land somewhere within that circle, and that's as accurate as we knew. And it had to land in that circle and not on the mountain itself, because that sky crane maneuver requires us to have a nice, flat place. If we landed on a hill slope and the rover tipped over, we'd have no way to get back up on our 6 wheels. So the rover landed in that oval there, and this was an interesting place we knew going in because we could see this blue outline of an ancient alluvial fan. A river had been flowing from the rim of the crater down to the bottom, delivering rocks from the rim of the crater and depositing them in that alluvial fan. So we knew very soon after landing we might have a chance to explore that. Now let me show you what Curiosity saw as it was landing. I showed you that in the animation that there was a camera on the belly of the rover pointed down. This is the real footage from that camera as the rover was landing. This movie started in darkness because the heat shield was in front of that camera, and that's the heat shield you can still see falling away down towards the bottom of Gale Crater. And you can see that the image is swaying back and forth ever so gently, and that's because the rover right now is falling on that parachute and swaying back and forth as it falls towards the surface. Now here we are getting closer and closer to the surface. By this point, that jetpack has started firing, and the sky crane maneuver is about to begin. Getting very close now. You can see some distortion from the heat from the thrusters. And the surface is just going to come up and jump at us in just about a second. Now, as the rover gets really close, you'll see the wheels deploy. There's the wheel. And there we are at touchdown. And those pebbles you see on the ground are smaller than half an inch. Now here are some of the first images taken by the cameras at the top of the rover's mast. Surveying the landscape, we landed in that nice flat spot at the bottom of the crater. Zooming out, you can see the shadow of the rover itself, the first rover selfie, and that was the mountain, that 5.5-kilometer high stack of rocks in the background. And here's the first true rover selfie. This is the first image Curiosity took with the camera at the end of its rover arm, turned back looking at itself. That camera still had its dust shield on it, so we get this nice sepia tone look. After that, the dust shield popped off and we were able to get clear, beautiful images that I'll show you in a couple of secs. So here are some of the first images that we took in detail of that landing site. And the geologists in the room are immediately going to notice that the small pebbles within these rocks are pretty round. And to the rest of us, this rock kind of looks like concrete. But the roundness of those pebbles within the larger rock told us immediately that those pebbles had to have been transported in water. Those pebbles must have tumbled down a stream bed in order to get that nice round shape. And so we knew almost immediately that we had landed in an ancient stream bed on Mars. Very exciting. But we saw something better on the horizon. So on the drive towards the mountain, we stopped in this area called Yellowknife Bay, which was a local low of very thinly layered rocks. And so here's a look close up at some of these rocks. Sandstone rocks showing prominent cross-bedding. And to geologists, this signifies a type of rock that we associate with rivers and sands that have been transported in water. So again, we're already getting hints very early on in Curiosity's mission that this was an interesting place. Now at the bottom of this bay, Yellowknife Bay, the rocks down at the bottom were very, very fine-grained. And we got up to look at them closely. We saw that there were these interesting textures. It almost looks like mud cracks. And in fact, when we reached out with that rover arm and drilled into the rock here at the bottom of the bay, this was what our drill hole looked like. Now this image is really important for a couple of reasons. First of all, the grayish rock powder that you see around the drill hole, that was ground up by the rover arm in the act of drilling that hole. And we can get a sense from those drill tailings, we call them, just how fine-grained this rock is. And we knew from drilling into the rock how hard the rock was. It actually wasn't very hard at all. We drilled this hole in just a couple of minutes. We had expected it to take a couple of hours. So this turned out to be a very soft mudstone. Now, mudstones are very exciting to planetary geologists because they typically only form at the distal ends of rivers or in lake beds. So we knew that this was not a sandstone that could have been formed by sand blowing in the wind. This was not a bunch of pebbles that was in a stream. This was most likely rocks that had formed in the bottom of a very quiet ancient lake. And the color of this rock was also really interesting. Mars is the red planet. Just about every single rock we had ever looked at, inside or out on Mars, had been some shade of reddish brown, indicating that the iron was rusted, oxidized iron. This was the first rock that we looked at the inside of it and saw a grayish, bluish, greenish color. That told us immediately that the iron in this rock was not oxidized, that this rock formed in a much different environment from all of the rocks we had previously discovered. So just by looking at this picture, we were already chomping at the bit. And when we fed that sample of the rock into the rover's sophisticated instruments, looking for organic molecules, this was the only place we found them. So I won't go into the details of this plot, but know that the green bars show the composition of the organic molecules found in this drill sample. Compared to every other place we had drilled on Mars, this was the place where we had the strong signal of organic molecules, the building blocks of life. So this was the first undetected detection on Mars of organic materials being preserved in an ancient environment that was one very similar to environments where we find life on Earth. So this was the first detection of a habitable environment on Mars. And there was other evidence too. The mineralogy of these rocks told us that the rock was about 30% clay, phyllosilicate minerals. And these are minerals that require water to form. These are minerals that require not only a lot of water, but water that is not too acidic. So this was another indication that this environment that we were studying on ancient Mars at one point looked something like this. Something like mud flats in a shallow, quiet lake, and a place with water that was not too acidic, not too salty, and a place with water that might have been around long enough to be a good environment for life to thrive. So this was one of the huge results coming out of the mission. And here is a full rover selfie taken at this spot. You can see two little dots down in the lower left of the image. Those are the holes that Curiosity drilled into and found the organic molecules. But this is a full selfie taken with that camera at the end of the rover's arm, turned back and looking at itself in its playground. So where's Curiosity going next? This was just a detour on the way to the good stuff. The good stuff we always knew would be at this mountain here. And we knew that this mountain had this huge stack of layered rocks, and we've already started identifying some of the geologic variations within those rocks as you go up. And I want to show you some pictures of that mountain with the 3D glasses. So stick those back on. And I'll show you a few of my favorite 3D images that Curiosity took that have that mountain in the background. So here's the rover at that Yellowknife Bay site, drilling into its first rock, the first detection of a habitable environment. And there's Mount Sharp, 5.5 kilometers high in the background. This is where Curiosity was this time last year at a place called the Kimberley, looking at another stack of layered rocks that we are still trying to figure out. We're just starting to write the papers on this area in the next couple of months. And here's the mountain again, Mount Sharp, behind some beautifully layered sandstone rocks at that same Kimberley region. Okay, glasses off. Going back to 2D, I'll just quickly show you some of our most spectacular, highest resolution images of this mountain. This mountain is still about 5 kilometers away, where it starts sloping up. We believe that where we are with Curiosity right now are some of the sediments at the very, very base of the mountain. But we still have a long way to go before we start climbing up to the top. So here's a look at some of those first layers towards the bottom of the mountain. And here's a look a little further up at some of those layers closer to the top. And I like this image a lot because it comes with its own scale bar. So you may not be able to see it here, but in the middle of that white circle, there's a teeny little black speck, and that's a boulder that's the size of the Curiosity rover, 10 feet tall. So you can imagine now that when Curiosity is over there, looking up at those foothills and up the mountain, the images are going to be spectacular, unlike anything we've seen before. And I'm going to encourage you to follow along because Curiosity should be getting to that vicinity of the mountain in about 1.5 years. Here's what the rover was doing yesterday. This is an image that Curiosity sent back to Earth this morning. This is the rover's arm stretched out, taking a close-up look at some really interesting mineral veins that we are still trying to figure out. This is brand new stuff. This is where the rover is today. And this is one of those first images to come down this morning of those mineral veins that we're looking at. We think these mineral veins might be gypsum that's cut through a mudstone rock. But again, very new stuff. So I'm going to encourage you to follow along with everything that Curiosity is doing, because this is not NASA's rover. This is not my rover. This is not a rover for scientists. This is your rover. All of our taxpayer dollars have contributed to this mission, and all of the data is publicly available. So I'm going to encourage you, if you're interested in what this rover is doing at all, to check out this website sometime. This is mars.jpl.nasa.gov/MSL. This is where every single image from the rover's engineering cameras and that beautiful color camera at the end of the rover's arm, these images get published on this website immediately after they're downlinked from Mars. I don't get to see these images any sooner than you do. I know some of you were impressed that I showed you an image that came down from Mars this morning. You shouldn't be impressed. Those images are yours just as soon as they are mine. So you can go to this website, you can look at all the new images as they stream in. And I'm also going to recommend my favorite website put together by an amateur fan called midnightplanets.com. And what this website does is it pulls all of those new images from JPL's official website and just displays them. So you can get a quick thumbnail glimpse of every single new image that's come from Mars. And you can see what came down most recently this morning were a bunch of color pictures from the high-resolution hand lens imager at the end of the rover's arm of some of those interesting mineral veins I just showed you. So bookmark this site. Check it out with your morning coffee every day. Make it part of your routine. This is your rover. So what's coming next? I argue that the most important thing we can do to better understand Mars, to continue down this path of knowledge that we've started, is to bring Mars back to Earth. These rovers are doing incredible things. They're teaching us a lot about the surface of Mars, about the history of Mars, about the potential for life to have evolved on Mars. What these rovers cannot tell us is definitively if there is evidence for fossil life in the rocks, if there are biosignatures, evidence that life definitely emerged. That is the kind of extraordinary claim that there was life on Mars that's going to require extraordinary evidence. And we can really only do that here in laboratories on Earth. The Curiosity rover is the most state-of-the-art spacecraft on Mars right now. It has an incredibly sophisticated suite of instruments. They're all already obsolete. That technology is 10 years old. If we want our exploration of Mars to keep pace with advances in technology, then we really need samples here on Earth so that we can study them in Earth laboratories. We also need samples here on Earth for the sake of repeatability. In science, an observation is really only valid if it can be repeated by multiple observers. And we can't do that with one rover in one location on Mars. If we were to find evidence for fossil life in a rock that came from Mars, we would want to repeat that experiment with multiple instruments in multiple laboratories, because what if it was just a calibration error telling us that there was a biosignature in a rock? It's extremely important that we get samples from Mars back here to Earth. So why haven't we done that yet? Well, it's really hard. I told you that it's really hard just to land something on Mars. But to bring anything back from Mars, not only do you need to land successfully on Mars, remember about a 50% success rate, then you've got to collect samples and store them. Store them in such a way that they're not going to get contaminated, they're not going to get fried by radiation, they're not going to experience temperatures that are too high. You have to store them and pack them up and get them ready to go back to Earth. Then you have to send a second spacecraft to Mars to grab that bucket of samples and launch them away from Mars. We, right now, don't have the technological capability to send a single mission to Mars that can collect samples, launch them away from Mars, and all the way back to Earth. Right now, we envision doing this as a three-stage process. First, you send your sample collection mission. Then you send a sample launch mission to get them away from Mars and into orbit around Mars. Then we have to send a third mission to Mars to rendezvous in orbit around Mars, slingshot around the planet, and bring them back to Earth. And then you have to make sure that they land gently on Earth, hopefully a little more gently than the Genesis spacecraft did here. So it's a hard process, and it's a long process, and it requires a multi-year, maybe several decade-long commitment of this series of missions to make it happen. The good news is we've got funding in place and a plan in place to do the first step of that. The next rover going to Mars, launching in the year 2020, so new it doesn't even have a name yet. We just call it Mars 2020. This rover is going to look like a twin of the Curiosity rover, except inside it's going to be much different. It's not going to be the same kind of science laboratory searching for evidence in place on Mars for organic chemistry. This rover is going to be a sample caching rover, meaning it's going to identify and collect the most promising samples around its landing site on Mars. So this rover is in the works now, and I'm fortunate to be part of the team that is designing, building, calibrating, and eventually operating the cameras for this rover on the surface of Mars. So that's called the Mastcam Z team, and these are going to be some of the best cameras ever sent to Mars. It's going to be a system of 2 lenses that can take wide-angle images and then zoom in for incredibly high-resolution stereo imaging of the planet Mars. So right now, we're in the process of designing what this rover is going to look like and how its instruments are going to function. And we're also in the process of deciding where on the planet we should send this. And that's a really difficult question. So imagine that you are an alien and you've been studying the planet Earth with some orbiting spacecraft. Maybe you've sent a couple of dinky rovers to the surface of the Earth. And you finally have your one chance to go land on the Earth, collect about 20 rocks from a distance of a maximum driving distance of about 10 kilometers. And you get to bring those 20 rocks back to your home planet and study them. But there's no guarantee that you're going to get a chance to bring back rocks from any place else. So where would you go on the planet Earth to collect 20 rocks within a distance of 10 kilometers that would tell you as much as possible about the entire geologic history of the Earth and the entire history of anything that had ever lived on the planet Earth? Where would you go? It's really tough. I asked this question to my planetary geology class a couple of months ago, and my favorite answer was the Grand Canyon, because you can land on the edge, rappel down the side of the canyon, grab rocks out all the way down as you go, and sample a huge period of Earth's history that way. That's a great idea, except engineering would rule that out immediately. So we have a bunch of rules we have to play by. We cannot land too close to either of the poles. We have to stay near the equator. And that's mainly because the rover has to be able to keep itself warm in order to survive. It's warmer near the equator. We cannot land at the bottom of any canyons because it's too windy down there. We cannot land at the top of any mountains because the atmosphere is too thin up there. We cannot land any place that's really bumpy because we're going to use that same sky crane landing system, and it has to be a safe place to land. So we have all these restrictions on top of having to decide the one place on Mars that's going to give us the most information from the rocks we bring back. So this is a question that my graduate students at Western Washington University and I are going to start addressing this summer. We're going to start doing some very detailed analyses of different candidate landing sites on Mars, and hopefully to be able to make some recommendations to NASA as to where might be the best place to send these missions. So it might be a place like Marth Vallis, one of the oldest terrains on Mars. This is a place where the rocks may be as old as 3.8 billion years old or older, a place that might tell us a lot about that early period in Mars's history. Or maybe NASA will send the rover to a place like the Eberswalde Delta. This is the site that came in number 2 for the Curiosity landing site process. This is the site where we have an ancient river delta, pristinely preserved. And river deltas require a lot of water to form or a lot of time in a lake. So this might be a good place to look for evidence for life having formed in a long-lived river system. Or another candidate site is the same landing site that the Spirit rover went to. Spirit found incredibly compelling evidence for a possibly habitable environment Don't know for sure. But it found evidence for hot springs having been present there. It found evidence for the mineral silica precipitating out of those hot springs. And we know that silica precipitation is a great way to preserve evidence, fossil evidence for life here on Earth. The Spirit rover also found evidence for carbonate minerals that may have formed in an ancient lake on Mars. And we also have the advantage at this site of going up and taking a look at the Spirit rover itself. Spirit died after 7 years of exploring Mars. It's still there on the surface, though. And just imagine the selfie that we could take with Spirit in the background. So, are we ever going to get these samples back once this 2020 rover collects them and sets them down on the surface expectantly for the next mission to come pick them up? Well, there's no plans definitively on the books to go and retrieve those samples. There is no NASA mission, there's no funding in place by Congress to go and bring back those samples that this mission in 2020 is going to so carefully select. So if this is anything that you care about, if you want to see samples from Mars be brought back to Earth in your lifetime, I encourage you to contact your representatives and tell them to support NASA's Mars exploration program, because they need to hear just how important it is that we get these samples back to the Earth. And then eventually, hopefully, we'll be studying Mars in person on the surface of Mars. I'm part of an analysis group at NASA that is defining the science objectives for human exploration on Mars, working under the assumption that humans may be able to get to Mars in the year 2030. We'll see if that happens, but NASA is taking this issue seriously enough to be defining already what kind of science experiments the humans are going to do on Mars, and how humans and robots are going to work together to get the most information possible that's going to help us answer these big questions about the ancient history of Mars and the possibility of life on the surface. So I'm going to leave you with that thought, and I have some time to take questions, and I'm going to encourage all of you to come up when we're done with the Q&A and get your hands on some of these spacecraft pieces that I've brought to share with you. We've got a piece of the parachute. We have one of the nylon ropes that was one of the cables that lowered the rover down in the sky crane maneuver. And we have one of the bolts that cut that cable when the jetpack flew away after the sky crane maneuver finished. So thank you all very much for your attention, and I'm happy to take your questions.
Hello, I have a couple questions. The first is, will you need to design a new landing system for the 2020 rover, or are you just going to use the same one as Curiosity?
Yeah, we are going to use the same landing system, so the exact same sky crane that you saw. We're hoping to add some improvements. I showed you in that image of Gale Crater, there was the big circle that was the landing ellipse for the rover. We're hoping to add some improvements to the landing system that are going to shrink that considerably, which means that'll open up some more interesting places for us to land. But it was really the success of that sky crane for Curiosity that allowed this new mission in 2020 to come about.
Okay, thank you. And my second question was, if you wanted to take good core samples of Mars, is that something that you could feasibly send robotics to do, or would you need to do that manually by sending a manned mission?
That's a great question. So the Curiosity rover has actually taken the first core samples on Mars from a depth of a whopping 6 centimeters. So that we know we can do on the surface of Mars. The European Space Agency is sending a rover to Mars in the year 2018. It's going to be called ExoMars, and that rover is being designed for the capability to drill to a depth of 2 meters. Now, ideally, we'd want to drill even deeper than that, because it's really in the top 3 meters or so of the surface of Mars that radiation can damage the organic molecules in the surface. So if we really want to find the best preserved evidence for life, we think we need to drill deep. And I think that's where humans and robotic drills are going to have to work together on the surface to really be able to do that well.
What is the composition of the atmosphere?
Yeah, the composition of the atmosphere is about 95% carbon dioxide. And so when I tell that to classrooms, they say, well, why isn't Mars warmer? That's a greenhouse gas. And I say, well, because it still is 100 times thinner of an atmosphere. There's lots of carbon dioxide, just not enough of it for greenhouse warming to take over.
Well, I can think of dozens of curious questions, engineering and like, but you're a geologist, your specialty is in those rocks. Particularly you yourself, what are you looking at?
Yeah, so what do I do with all of this? I work on the camera teams for the Spirit and Opportunity rovers and now the Curiosity rover. Now I'm helping develop the cameras for that next 2020 rover. So my expertise would be what you call imaging spectroscopy. So our cameras on these rovers can take pictures in wavelengths beyond what the human eye can see into the near infrared. And those are the wavelengths of light that have the diagnostic absorptions of a lot of iron-bearing materials. And we can also see evidence for hydrated minerals. We can see evidence for water in the structure of rocks with those cameras as well. So what I do on these rovers is use the pictures that we take on the surface in multiple wavelengths to help constrain what the mineralogy is, what the rocks are made of that we're looking at on the surface, and looking for the rocks that show evidence for hydration, evidence for having interacted with water at some point in their history.
As a geologist, usually a lot of them end up in finding minerals on Earth for resources. Are there resource minerals on Mars that could be used by future colonists, possibly?
Yeah, that's a tough one. Not enough to make it really financially viable for us to go there and mine them, but there's certainly plenty of iron. It would be a great place to go look for iron ore. And when we talk about resources on Mars, usually what we're talking about are resources that humans could use to help sustain themselves on the planet. So a great resource that we keep looking for and keep thinking about how to tap into is water. And we know that there's water ice at the poles, and we know that there's water ice as ground ice even at lower latitudes as well. So those resources for sustaining humans on Mars is really where a lot of that effort is going today.
If water flowed on Mars in the distant past, what happened to it? Was this due to a weak gravitational field?
Great question, and I did not give you an answer to that because nobody knows. I will give you a couple ideas that the community has about where the water might have gone. So we know today Mars has no magnetic field, but there's some evidence in the rock record on the surface of Mars that in its past, Mars did have an active magnetic field. And the magnetic field might have been able to protect a thicker Mars atmosphere from being stripped away by the solar winds. And so that magnetic field could have shut off at some point in Mars's history, and then the atmosphere would be slowly lost to space after that. That is exactly the question that the MAVEN spacecraft, which recently arrived at Mars, seeks to answer. That spacecraft is going to orbit Mars and sniff the upper part of the atmosphere, measure the isotopic ratios of deuterium and hydrogen, and try and answer this question of, is Mars's atmosphere in a process of actively escaping? How long has that process been going on? Another theory is that maybe Mars lost its water and most of its atmosphere in a giant impact event. As a planetary geologist, whenever there's a mystery in the solar system we don't have an answer to, we say something hit it. Why does Venus spin so slow and backwards? Something hit it. Why does the top half of Mars, the northern hemisphere, why is it so low and smooth? Something hit it. So where did Mars's water go? Something hit it. But these are the big questions in Mars science today, because there is not enough water ice stored at the poles and stored under the surface as ground ice to explain the massive volumes of water that were required to carve these enormous channels on the surface.
Hi. So I don't know exactly how large Gale Crater is, but it looks pretty big. And given that it was formed before this alleged lake that was there, how do we rationalize that time scale with the crater forming beforehand, before the lake was there, with the atmospheric composition of a crater being able to be formed that large from an impact that wouldn't have been broken up?
Right,
Beforehand.
right. So if the crater formed in a time when Mars had a thicker atmosphere, why didn't that impactor burn up in the atmosphere before it hit Mars? We know that a lot of the impactors coming down to Earth just burn up in the atmosphere, don't even make it all the way to the ground. And the answer is it would have been a really big impactor, big enough that it wouldn't have burned up in the atmosphere. And we know that there were lots and lots of really big impactors floating around in the very early solar system. So in this time period that we're talking about, when we think this crater formed, older than 3.8 billion years ago, maybe older than 4 billion years ago, there was a lot of debris kind of left over from the formation of the solar system, a lot of big space rocks smashing into each other. The early solar system was a very violent place, we think. And so it would have just taken a very, very big impactor to punch through that atmosphere, form a big crater.
So this is assuming that the atmosphere of Mars at that time would have been large enough or thick enough to allow a large body of water to form and not have enough vapor pressure to evaporate
Yeah, and
off.
so you're getting at a point that I didn't specify, so I'm glad you brought this up. Today, on the surface of Mars, the atmosphere is too thin for liquid water to be stable on the surface. If you were to teleport a bathtub full of water to the surface of Mars, it would boil away because the atmosphere is so thin. The laws of physics won't allow liquid water with an atmospheric pressure that low on Mars. So we know water had to have been flowing on Mars at some point in its past in order to carve these spectacular channels that we see. So Mars in its past must have had a thicker atmosphere then. And so then where did that atmosphere go? Where did the water go? That gets back to the previous question, and maybe it was this atmospheric escape after the dynamo shut off and the magnetic field of Mars turned off. But those are really the big questions. And understanding how Mars's climate changed from a more Earth-like environment to this cold, dry, desiccated environment, that's a hugely important question in comparative planetology. So the Earth is sometimes referred to as the Goldilocks planet because it's not too cold, it's not too dry, it's not too hot. And Venus is the other extreme. Mars is on one side, Venus is on the other, with a runaway greenhouse effect, with an atmosphere that is hot enough to melt lead on the surface of Venus. So our three planets in this little neighborhood, Mars, the Earth, and Venus, are a great example of the possibilities of what can happen to a planet.
You talk about the looking for water. Could it be another liquid?
Yeah, that was hotly debated. When those first pictures of the channels flowing across Mars came down from the spacecraft, does it have to be water? Could it be liquid carbon dioxide? Could it all have been carved by lava? Could they all be lava channels? Could there be rivers of beer on Mars? This was a debate for a long time, and I think what's really sealed the nail in the coffin for water is the evidence from the mineralogy that we've been able to get from our spectrometers in orbit around Mars and from our rovers on the ground. These rovers and spectrometers see the evidence for water molecules that are still preserved in the mineral structure of these rocks. And that tells us that it had to have been water.
Okay. So I'm understanding that something can penetrate the atmosphere and strike the surface of Mars easier than Earth, correct?
Today, definitely. We don't know how thick Mars's atmosphere was in the past. It could have been as thick as the Earth's, or it could have been still somewhere between what Mars is now and what the Earth is.
Is it, I have no idea, is it easy to tell the difference? Is like a sample being from Mars all the time, or could it be a foreign object? Is science able to tell the difference between a foreign object on the surface of Mars versus something that's always been there?
Yeah, that's a great question. How do we know that all the rocks on Mars are from Mars? And the Opportunity rover was the first rover on Mars to discover meteorites on the surface. And Opportunity has studied a couple of really quite large rocks that are nearly pure iron and nickel. And iron and nickel are rocks that really only come about from space. So iron-nickel meteorites, the Opportunity rover has found. Curiosity found some a little less than a year ago as well. So we do know that there are rocks from space that are on the surface of Mars. And I'll just note, because I have this slide at the ready, we also have rocks from Mars that have made their way to Earth. So I talked about the need for going to Mars and bringing samples back. Mother Nature has done that for us a couple of times. Some of those giant impact events that occurred on Mars sprayed ejecta, rock fragments, out into space. And some of those rock fragments that were freed from the surface during that impact event have traveled through space and have eventually landed on Earth. And we know that we have a couple of these in our meteorite collection. And we know that because there are teeny gas bubbles entrained in these rocks, and those gas bubbles contain a perfect match to Mars's atmosphere. So no other place that could have come from but Mars. So this is the most recent one, a meteorite called Black Beauty that was identified as from Mars. And this is the most famous meteorite from Mars. Every planetary geologist must memorize this number, Allen Hills 84001. This meteorite got a lot of news in the 1990s because scanning electron microscope images revealed these little tube-like structures inside the rock. This is smaller than the width of a human hair. Teeny tiny structures that can be explained by purely mineralogic processes, but they look enough like microfossils that they've gotten a lot of people excited about the possibility of microscopic fossil life being preserved in these rocks. It's still a controversy. I'm not convinced, but I think that this is compelling evidence for why we need rocks from Earth, from places that we get to select on Mars, why we need those rocks here on Earth to do this level of detailed analysis with them. We don't know where on the surface of Mars this rock came from. We don't know where this rock came from either. But if we could go to Mars and select the best sample set to bring back to Earth and do those analyses, then we'll be getting somewhere.